The next important concept in quantum computing would be density operator. Okay. What exactly density operator is? Before going to that, there is one definition that we will see, that is, if there exists an orthonormal basis, get UI. Orthonormal basis means whose inner product. If I consider inner product of get UI, of course, UI, UJ, I will say, inner product, if I say, it is equal to 1 for I is equal to j, 0 for I not equal to j. Okay, this is the definition for orthonormal. Whether it is in a normal vector space or in a quantum vector space. Okay, so if there exists an orthonormal basis, get ui for I is equal to 1 to n, something like that, then we can expand the state get xi in that basis as follows. How we can expand? Just see, c1 get u1 plus c2 get u2 plus and so on plus cn get un. Okay, of course, there's one rule called Born rule in quantum. Born rule of finding probability. If I can express a state in this format, I mean, in terms of orthonormal vectors, then what Born rule says is of usually Born rule is for probabilities. Probability or probabilities. What Born rule says is probability of finding a system in ket ui is given by, we have already seen this in one of my previous videos, but anyways, sorry, this CIs are, by the way, I should tell some certain things. Yeah, CI squared. Okay, I should say here CI belongs to complex plane. Okay, so now probability of finding a system in ket UI state is given by probability of finding a system in ket UI. Of course, ket UI is nothing but the state, but if at all, if that word is asked, nothing to get confused, is given by mod CI squared. Since CI is a complex number, it is nothing but CI into, of course, into CI conjugate. Okay, CI into CI conjugate I will be doing. Okay, this is an important thing again before going to the projection. Of course, density operator. Density operator is nothing but projections, by the way. Okay, yeah. Density operator. Density operator. Density, usually we use rho to denote density. Density operator for a state, for a state ket xi, rho would be given by this value. Yeah, I think you would have recollected. This is nothing but the outer product. Okay. Now, density operator, there are certain things that if the trace of rho is 1, then it has unit trace and all the things are there. We will see that. Density operator, it's also called the projection operator as well. Okay. Now, just see the matrix notation for density operator. Matrix notation for rho. Okay. How I will write, just see here. Rho u2 UIs I have defined in terms of UIs now. U2 row U1, U2 row U2. Okay. This is how I will write. Okay. Suppose in continuation, I'll just make a mention of one small thing and do what is needed. Expectation. Expectation value. All of us know what is expectation. Expectation is nothing but mean kind of thing. Okay. Expectation value of an operator A in terms of density. How do I write it as in terms of density operator is, I write like this, trace of row A. That's how expectation value is defined. Okay. Of course, probabilities anyways I have seen. Just see how to find, we will just see how to find the density operator. One numerical on it. Okay. Given ket xi, this is equal to 1 by root 3 ket u1 plus I root 2 by 3 ket u2. Okay. Ket uk constitute orthonormal basis. Constitute orthonormal basis of orthonormal basis of ket xi. All those are not needed. And why to confuse? Find the density operator, find row, and trace of row is the question. Okay. Let's see how to solve it. Now, what would be the matrix notation for it? Since I am being given in U1 and U2 now. So how will I write? Just see. How will I write? How will I find the density operator? First, finding the density operator and then writing it. Okay. What is density operator? It's the outer product, right? So let's find the outer product. For finding the outer product, what do I need? Always, guys, understanding is easy, but writing is only difficult in quantum computing. Okay. I already have ket xi. I'll be needing its dual. Okay. What's its dual? It's nothing but the transpose, right? So 1 by root 3 dual of u1. I is there. Conjugate of I would be minus I. Root 2 by 3 u2. Okay. Yeah. So what do I get? When I multiply both, what do I get? This into this. Okay. Why? Because ket xi is ahead. Okay. Yeah. So 1 by root 3 into 1 by root 3 becomes 3. Okay. Then what about multiplying these two? Ket u1. It's a dual of u1. Okay. Yeah. Plus I into minus I is my I squared or minus 1. Minus I squared. Minus of minus 1 is plus 1. Root 2 becomes, I mean root 2 by 3, root 2 by 3 becomes 2 by 3. U2 and U2. Outer product of U2. Okay. Now, he has asked us to write it in matrix format. So how do I write it? Okay, just see here. How do I write? In matrix format is 1 by 3 minus I root 2 by 3 I root 2 by 3 2 by 3. Okay. Now, what's the trace? Trace is nothing but this, of course, just a second. I have taken this one into this one into this one also I should take. Okay, that terms I have missed, because of which matrix is looking weird. Okay, 1 by root 3 root 2 by 3 would be what? Minus I root 2 by 3. Okay, u1 u2, inner product, outer product, I'm sorry. Okay, next this one into this value would give me what? Again the same thing, plus I root 2 would be there, and then 3 comes, outer product of u2 and u1. Unlike if it is orthonormal, inner product is 0, but nothing is told about outer product. So you can see here, you can see the matrix notation once. I have u1 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 u2 u2 u1 u2 u2. Okay, so just see here, u1 u1 coefficient is 1 by 3. Okay, 1 2 coefficient is minus I root 2 by 3, as it is here. 2 1 coefficient is I root 2 by 3, I root 2 by 3. 2 2 coefficient is 2 by 3. That's how I have written the matrix format. Now find the trace. Trace of row is nothing but sum of diagonal elements, which is 1 by 3 plus 2 by 3, which is nothing but 1. Okay, always a density operator has unit trace. That's what. Okay, yeah. Now if you are asked to find for another example, ket xi, this is equal to 1 by 2 ket u1 plus 1 by root 2 ket u2 plus 1 by 2 ket u3. How do you find row and how do you find trace of row? This is the, show that trace is equal to 1 can be the question as well. This is the question. Just try to find out. I'll leave this for you to just check. Now, there's one more question. Given row is equal to 1 by 4 minus 1 minus I by 4, 1 minus I by 4, 3 by 4. Okay. Question has been asked. Is it matrix for density operator? Matrix for density operator. Okay. Now, see the trace. Trace of density operator is always 1. So, see the trace 1 by 4 plus 3 by 4 is 1. But then there's one point which I thought I will tell in the beginning only, but I will make a mention of it in this problem. What that is if you look at the matrix is not Hermitian, guys, not Hermitian. What? Row is not Hermitian. What is Hermitian? Hermitian, skew Hermitian, unitary. They have some relationship with symmetric, skew symmetric, and orthogonal matrices. Okay, here all the operators that I have considered, x, y, z, all those are Hermitian. Okay, and unitary as well, guys. But then, of course, including this density operator, it should be Hermitian. Of course, I have not discussed it. I can do a video on that. But then they are Hermitian as well as unitary. Here, row is not Hermitian is what I'm trying to say. Why? Let us see. Okay. If it is Hermitian, what is symmetry? A is equal to A transpose. Okay. If it is Hermitian, then A should be equal to A conjugate transpose, because Hermitian, skew Hermitian, unitary are all defined for complex matrices, guys. There is nothing like transpose. Always for a number, complex number exists as conjugate. So you should take the conjugate of it and transpose. Okay, now if I go with conjugate of row, what do I get, guys? 1 by 4, 1 plus I. Conjugate is nothing but Opposite sign for the imaginary number. 1 plus I by 4, 3 by 4. Okay. Do the transpose. Row conjugate transpose. See what happens. 1 by 4, 1 plus I by 4. Perfect. But the other one is 1 plus I by 4. This is also perfect. 3 by 4. Okay. Yeah. So here what am I getting? Row is equal to row conjugate transpose. Yes, sir. No. Why? Because see the complex numbers. Imaginary part there is negative sign. Here it is positive sign. So row is not equal to row conjugate transpose. Hence, given matrix is not density operator matrix. Why? Because it is not satisfying the property of Hermitian. Mind you, all operators are Hermitian. Okay. So this is all about the density operators. Of course, not all about. There's one more point that I will say, that is extension of little more things about the density operator. That is, yeah, what that is if I take if row is being given to me, then row square is equal to row. Okay, that also is satisfied. Also, yeah, guys, there is one more note about row. This is very important. That is summation I pi probabilities. Okay, should be equal to identity matrix. This is called completeness relation. Completeness relation. Okay, what that is suppose if I take the probabilities, P probabilities, if I take, okay, yeah, I is equal to 1 to m. It's defined like this. Now, summation of all PIs should be equal to I. There's one example which I'll do to make you understand this. Suppose if I define P naught to be ket 0, I mean outer product of 0, ket 0, P1 to be outer product of ket 1. Okay, check the completeness relation. Okay, now you see outer product, as mentioned in my previous videos, is always a matrix, right? So what would be this? This is 0, 1. This is, no, this is not 0, 1, 1, 0. I always say get 0 and write 0 first. Okay, this is a printing mistake. 1, 0, 1, 0. And this would be what? 0, 1, 0, 1. Okay, so multiply both. 1 into 1 over 1 into 0, 0 into 1, 0 into 0. Okay, this is P naught. What's P1? 0 into 0, 0 into 1, 1 into 0, 1 into 1. 0 into 0, 0 into 1 is also 0. Okay, now what is completeness relation is P naught plus P1. I will do 1, 0, 0, 0 plus 0, 0, 0, 1. So adding this, I get 1, 0, 0, 1, which is my identity matrix. That's what is completeness relation. What that is if I find the projection operators, projection, P is nothing but my projection operator. Okay, projection operator is also, density operator is denoted by row. Density operator is denoted by row. Okay, Projection operator also stands for projection operator. P is nothing but outer product of two kets. Projection operator, it's operator, so it is Hermitian. Okay, of course, P square is equal to P as well. That means what? P square is equal to P means what? P is normal as well, normal. Okay, and then P is nothing but sum of all outer products. Okay, and then summation IPI, this is equal to capital I. This is nothing but my completeness relation. Okay.